and a 1, and a 2, and a 1, 2, 3, go. Okay, so Bellwork says the system of equations above has a solution x, y. What is the value of x? And we're given 1/2 y is equal to 4, and then x minus 1/2 y is equal to 2. So I have both equations here. Okay, this goes back to your solving systems of linear equations. Remember, you have 3 different ways to do it. You have the elimination method, which this one is set up perfectly for, the substitution method, or graphing. The only one that I'm not going to show you today is graphing. Okay, you'd isolate the y variable, plug it in an xy coordinate plane. There you got your graph. So the elimination method first, what it requires you to do is to have 2 coefficients with the same absolute value associated with the same variable, but you want them to be opposite. So here I have 1/2 y, and in the second equation, I have a negative 1/2 y, or x minus 1/2 y. What that allows me to do is add these equations straight up and down. 0 plus x just gives me x. 1/2 y plus a negative 1/2 y is going to bring me back to 0. 4 plus 2 is going to give me 6. X plus 0 is equal to 6. Therefore, x must be 6. Okay, that's the elimination method. If you chose to do it substitution method, you'd have 1/2 y is equal to 4. X minus 1/2 y is equal to 2. Substitution method requires you to solve for one variable, so either x or y, and then we plug it back in to find out what our other variable is. So this top equation is pretty simple to solve. So 1/2 y is equal to 4. I want to isolate the variable, so I would have to divide by 1/2 on each side or multiply by 2, however you want to look at it, because those are equivalent measures. So y is going to be equal to 8. Okay, and then I take that 8 and I plug it in for the variable in my second equation. So it's x minus 1/2 times the quantity of 8 is equal to 2. Okay, 1/2 times 8 is 4, so that's x minus 4 is equal to 2. Add 4 on both sides to isolate the variable, and you're left with x is equal to 6. Both methods, real nice and quick. Both yield the correct answer, which corresponds to D. Graphing, I wouldn't necessarily graph either of these because, one, graphing takes time, and secondly, it's an approximation. Okay, in the SAT situation, we want to be quick, we want to be efficient, and we want to get stuff done as quickly as possible. So that means choose an efficient method. All right, let me upload the sides. All right, 5-minute check. First question says, find the exact values of sine of theta, cosine of theta, and tangent of theta if the terminal side of theta in standard position contains the point at 3, -4. So the first thing we want to do here, draw an XY plane, plot that point. 1, 2, 3, 1, 2, 3, 4. Okay, right there. Okay, from there, I've drawn my terminal side and I've intersected that point. Okay, from here, remember this is the theta that we will be using. It's what's known as the reference angle. It's always between the x-axis and the terminal side. So that makes our 90-degree angle right there. Okay, from this, I can fill in certain values. The distance I had to move right on the x-axis was 3. The distance I had to move down on the y-axis was -4. Okay, I want to use those two to find the value of r by doing the Pythagorean theorem, which says that r squared is equal to 3 squared plus -4 squared. 3 squared is 9, -4 squared is 16. Add those together, you get r squared is equal to 25. Take the square root of both sides to find that r is equal to 5. Okay, now from here, since theta is there, I could look at it opposite side over adjacent, or hypotenuse, adjacent over hypotenuse, opposite over adjacent. Or I could remember that since we've gone to the coordinate plane, sine of theta is always equal to y over r. Cosine of theta is always equal to x over r. Tangent of theta is always equal to y over x. Okay? And if you think about it, the y value is the opposite side. The x value is the adjacent side. The r value is always the hypotenuse. Tangent, opposite over adjacent, so y over x. Now I would just plug those in. So sine of theta is equal to a negative 4/5. Cosine of theta is equal to 3/5. Tangent of theta is equal to a negative 4/3. Bing, and that lines up because we are in quadrant 4 where cosine is the only ratio that is positive, cosine or secant with its reciprocal. So that's the first one. Good on that? Feel like I flew through that. All righty. Let's go on to the next one. Bang, bang, bang. Dang, I'm good. All right. Number 2. Find the exact value of cosine of 150 degrees. So that's cosine of really 30 degrees in all reality. But we don't got to tell anybody. Okay. So cosine of 150 degrees, first step, as always, is we want to draw our angle in standard position. So the initial side is the positive x-axis. The terminal side is going to rotate 150 degrees. And then we're going to find our reference angle. So got my xy axis. Bang, here's my initial side. Remember, this is 90 or pi over 2. This is 180 or pi. You're looking in radians. This is 270 or 3 pi over 2. This would be 0, 360, or 2 pi if you're looking for it in radians. So I'm rotating 150 degrees. That's between 90 and 180. So I'm going to say that it rotates right about there, 150 degrees. Okay, now the key to doing this is to find this acute angle, right, from the terminal side to the x-axis. And we call that the reference angle. Okay, so if this is 180 and they're rotated 50 degrees, to figure out this distance, I could just take 180 minus 150, and I would be left with 30 degrees. Okay, that's my reference angle. Okay, from here, I need to assign whether my cosine is going to be positive or negative. Okay, remember we have a nice little cheat sheet. It goes A, S, T, C, rotating clockwise. All trigonometric functions are positive in quadrant 1. Only sine and cosecant are positive in quadrant 2. Tangent and cotangent are positive in quadrant 3. Cosine and secant are positive in quadrant 4. If you think about that, it makes sense because sine is always the y value. So when I'm above the x-axis, y is positive, right? Cosine is the x value. So when I'm on the positive side of the y-axis, cosine is going to be positive. Tangent is the tricky one because it involves y and x. So to get into quadrant 3, I have to have a negative x value, a negative y value. Those two negatives cancel out to give me a positive. Okay, so from here, and using the reference angle, realize that this is the right triangle that I'm dealing with. Okay, so the cosine of 150 degrees is really equal to the negative cosine of 30 degrees. Okay, those are equal because they have the same reference angle. Reference angles allow you to take all of these trig functions because it always gives you an acute angle. So cosine of 30 degrees, that comes from your special right triangles, 30, 90, 60. Okay, so, and you would find that the cosine of 30 degrees is equal to the square root of 3 over 2, but it's a negative, so cosine of 150 degrees is equal to a negative square root of 3 over 2. Something like that. Okay, when they're talking about exact values, chances are they're talking about your special right triangles. 30, 60, 90, 45, 45, 90. At the very beginning, when we first started this, I showed you a chart, said it's going to be in your best interest to try to memorize that. It still is kind of in your best interest to memorize that. All right, so find the exact value of 3 pi over 2. I guess I could have left that. Leave all that stuff. I can just get rid of my terminal side here. Get rid of this here. And we are good. Okay, so I'm going to leave up my cheat sheet. I have cosecant of 3 pi over 2. Okay, so first we start in standard position. Okay, we start in standard position. Down here is 270 or 3 pi over 2, if you're looking at it in radians. So start at my initial side, pi halves, pi, 3 halves, 3 pi halves. Okay, if you look at this, this kind of puts you in an awkward situation because you don't have a quadrantal. You don't have an acute angle, right? It falls on one of the quadrants or one of the axes. So what we need to realize in a circle, if I were to just draw a circle, right, and I find my center, and I have the radius here, as I move around that circle, does the radius ever change? No, because that's the definition of a circle, right? I can spin that. I can't go farther, can't go shorter. The radius is always the same. So in this case, my R value or the radius value is always going to be equal to my Y value, right? Because they fall on the same one, right? Because that Y value is a point on the circle. It would be right here. So in this case, your Y value is equal to your R value. Well, what point makes sense and is easy to use that puts us on the negative y-axis? Well, for simplicity's sake, 0, -1, right? Okay, so cosecant is the reciprocal of sine. So if sine of theta is equal to y over r, cosecant, yeah, you can go. Cosecant of theta is equal to r over y. Well, my y value is -1. My r value is 1 because r is always positive. So cosecant of theta is going to be equal 1 over -1, which would simplify down to a -1. Awesome, awesome. Okay, this one's a little bit harder. says the tension in a pendulum string is modeled by T is equal to 20 times the cosine of theta. So to determine the degree of measure of the angle for T when it's equal to 0, 10, and 20. Okay, so this one, we're going to want to use a calculator. Okay, calculators are our friends. They're not food. So if I set it up, I have T is equal to 20 times the cosine of theta, and I'm going to plug in 0, 10, and 20 in for T. Okay, and then I'm going to solve, and then I'm going to use inverse cosine to figure out what the angle measure is. So when I plug in 0 in for T, 0 is equal to 20 times the cosine of theta. Just like any other equation, I want to isolate cosine of theta, so I'm going to divide both sides by 20. I'm going to be left with 0 is equal to cosine of theta. And then to solve this, what I have to do is I have to take cosine inverse, which is written like this, or inverse cosine. Okay? Once I do that, cosine inverse and cosine are going to be canceled out. I'm going to be left with theta on this side. But I need to plug in cosine inverse cosine of 0, and then that will give me my angle degree of theta. So I go to my calculator, second cosine, put in 0, and it gives me 90 degrees. So theta is equal to 90 degrees when T is 0. Okay, when T is 10, set up the same way. 10 is equal to 20 times the cosine of theta. Once again, I isolate cosine of theta by dividing by 20. 10/20 simplifies down to 1/2. So 1/2 is equal to cosine of theta. Take inverse cosine of 1/2. And I get that theta is equal to 60. So 90, 60. And now what is it when T is 20? Well, I still set it up the same way. I still solve it the same way. 20 is equal to 20 times the cosine of theta, divide by 20 on both sides. 20 divided by 20 is 1. Cosine of theta, so I have to take cosine inverse. So the cosine inverse, or inverse cosine of 1 is equal to theta. Inverse cosine, plug in 1, and I get that theta is equal to 0 degrees. So 90, 60, 0, which corresponds to answer D. Okay, this one, which of the following trigonomic functions are positive in quadrant 3? So sine, quadrant 3 is where we have a negative x value, negative y value. So sine is y over r, so negative 1 over r, or negative y. So in quadrant 3, sine is going to be negative. In quadrant 3, cosine is going to be negative. Quadrant 3, secant, which is the reciprocal of cosine, is going to be negative. And tangent is the only one that is positive. Okay, and that comes straight from your cheat sheet. A little ASTC revolving left and right. Okay, so previously we've evaluated trigonomic functions using reference angles. Okay, there was one on the check for 5. That's what we pretty much did last week. Today what we're going to do is we're going to kind of standardize it. Okay, because remember, the amounts of your trigonomic functions are ratios of side length. Okay, that never changes. Okay, and you have a right degree, you have a right angle. Okay, it's a ratio of the side lengths for it. So we're going to find values of trigonomic functions based upon the unit circle. And we're going to use the properties of periodic functions to evaluate trigonomic functions. What this sets up is known as coterminal angles. So first one is the unit circle. You have circular function. To look at a circular function, kind of think about the hands on a clock, right? So if you can imagine coming from noon o'clock, noon, and the hands on the clock repeat itself, right? Each hour, the minute hand does. Okay, it falls in that same position as it rotates around, and it just repeats itself every hour. That's how we tell time on an analog clock, right? Based upon the minute hand. The hour hand on a clock repeats itself every 12 hours. Well, why? Because we go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, noon, then we start back over at 1. So a clock is a perfect example of a circular function. Okay, you hit the same spot over and over again. And that sets up, and that's due to coterminal angles in this form of trigonometry. But if you think about the hands on a clock, it kind of helps relate it, or like pedals on a bicycle or a wheel on a bicycle. Okay, it hits that same position over and over and over again in relation to the ground. Okay, a periodic function. Okay, a periodic function is a circular function, meaning that it will repeat itself after a given period. So like with the minute hand of a clock, it repeats itself every hour. So it would have an hour period. Okay, one cycle or a cycle is how long does it take me to return? Okay, once I return to that spot, I've completed a full cycle. And then I begin the next cycle. And then I begin the next cycle. Okay, cycles, the period is how long it takes for it to complete a cycle. Okay, in our world, right now, we're dealing with 360 degrees and 2 pi. Okay, because as you come back around, you've completed 2 pi radians or 360 degrees of rotation. And then you just repeat to 720 and 4 pi. So here's an example of the unit circle. Okay, and I want to draw your attention to the points on the quadrantal angles. So you have 1, 0, 0, 1, negative 1, 0, 0, negative 1. So from this, on the unit circle, because this is the unit circle, what is the value of r? Well, the value of r is always going to be 1, right? Because the radius of this circle isn't going to change. Okay, it's going to stay the same. And since we know that cosine is x over r, if the value of r is 1, then our value for x is going to be equal to the cosine of theta. Okay, and the same thing with y. Since sine of theta is y over r, with r being 1, the value of y is equal to sine of theta. Okay, so if you look at it, we have a point P, xy, is equal to the distance of cosine of theta and sine of theta. So if theta was 120 degrees right here, so it would have a reference angle of 60, it would be the cosine of 120 would be that given point in x value, and the sine of 120 would be that given point in y value. Okay, why I have this, I'm going to give you a nice little cheat sheet. Okay, but I wouldn't call it little. This page occurs, it's page 622 in your book. Okay, and I highly recommend writing this down. Okay, I'm going to give you like 5-10 minutes, because when it's asking you to find the exact values, you can use this. Okay, and believe it or not, each one of these corresponds with the Pythagorean theorem. Okay, and I'll show you that in a second. So starting here, at 0 degrees, you can see it's 0.10. At 30 degrees, or pi 6 radians, my cosine value is square root of 3 over 2. my sine value is 1/2. Okay, 45 degrees, pi over 4, square root of 2 over 2, square root of 2 over 2. 60 degrees, pi thirds radians is 1/2 for cosine. Sine, it's square root of 3 over 2. Then I hit my quadrantal, where I'm at 0, 1. What's the chat say? That's fine. Hey, that's fine. I'm recording it too, so they can always watch it at home as well. So once I hit 120 degrees, you can see this would be a reference angle of 60. So if I go to 60, I'm in quadrant 2 where cosine is negative. So you can see how it's a negative 1/2, which is equal to the cosine of 60. And then my sine value is positive because I'm in quadrant 2, but it's square root of 3 over 2. But they match onto 60 degrees. And then at 135, they match to 45 just with the sign change based upon the quadrant. 150 degrees matches 30 degrees with a sign change based upon its quadrant. Cosines in blue, sines in red. So then you have -1, 0, and the cosine of 180 degrees, or cosine of pi, is -1. Sine of those is 180. And you can see that it repeats, right? 210, the reference angle is going to be 30 degrees. So you can see my sine and cosine functions have repeated themselves, just with a negative being associated because of the quadrant. Okay. Then I get 225, which is a repeat of 45. Again, just with the sign change. -1/2 and the square root of 3 over 2 with a sign change. Then I hit 0, then I hit my quadrantal. Now I'm operating in quadrant 4, where cosine is the only one that's positive. You can see that 270 is right there. 300 has a reference angle of 60, so it's going to map with 60. 315 has a reference angle of 45, so it's going to map with 45. And then just the signs are associated by the quadrant. 330, reference angle of 30 degrees. Okay, so that matches 30 degrees with the negative and positive being assigned based upon the quadrant. Okay, and like I said, believe it or not, if we were to use these, okay, and actually plug them into the Pythagorean theorem, we would always equal 1. So I'm going to pick a point that looks like it would be tough to do, and that looks like it would be, we'll say 45 degrees. Okay. (45) is the square root of 2 over 2. That's the given point. Yes, that's fine. You guys better do your independent study stuff, though. Okay, so it's saying at that point is a square root of 2 over 2. So if I really break it down, that means that this side length is equivalent to the square root of 2 over 2. This side length is equivalent to the square root of 2 over 2. And trying to prove that my R value is equal to 1. Okay, because the radius in the unit circle states that it should be equal to 1. Okay, so how would I do that? Well, I use the Pythagorean theorem, showing that R squared is equal to the square root of 2 over 2 squared plus the square root of 2 over 2 squared. Okay, if I break these down, this one here, square root of 2 over 2 times square root of 2 over 2, then multiply straight across. Square root of 2 times the square root of 2 gives me 2. 2 times 2 gives me 4. That simplifies down to 1/2. Same thing here. Square root of 2 over 2 times the square root of 2 over 2. Square root of 2 times the square root of 2 is equal to 2. 2 times 2 is 4. So that's equal to 1/2 plus 1/2 would give me R squared is equal to 1. If I take the square root, I'll find that R is equal to 1. Okay, and you can do that on any point, any given point. Why? Because these values of the trigonomic functions are ratios of the side lengths to the hypotenuse. Okay, it has to happen. You cannot have a triangle that has a 45-degree angle, right, where the ratio of the side length to the hypotenuse isn't square root of 2 over 2. It's physically impossible. Okay? If you get anything different than that, that means you don't have a 45-degree angle. Okay, so why, in the real world, why would that be useful? If I'm thinking like the pitch of a roof, right? You can draw the pitch of a roof based upon a right triangle, with your hypotenuse being this actual side, the height of the roof being here, and the width being down there. Okay, you cannot have that because of the, and it's true in the physical world too, okay, because they are ratios of the side lengths to the hypotenuse. That's all sine and cosine are. Sine is the opposite side, cosine is the adjacent side. All right, so hopefully that gave you enough time to copy that down, or if you took a picture, that's cool too. Just, this is a big thing, okay, it's huge. I'll give you just a couple more seconds to copy it down. Yeah, that's fine, Mila. And like I said, me and you are going to have to schedule some time to go over it one-on-one, right? To try to eat up the past 3 weeks. All righty. And away we go. Okay. So find cosine and sine given a point on the unit circle. Okay, this one is a little frustrating because it's not one of our standard angles. It's not a 30, it's not a 60, it's not a 45, right? Because if it was those angles, those ratios would repeat itself. Email me. Email me at thomasb.bsd29j.com. Okay, anytime you guys need to reach out to me, you do it over email. Okay. So it says the terminal side of angle theta in standard position intersects the unit circle. So that's a key point because it says that our radius is 1. It has to be. Okay, well, if the radius is 1 and the cosine and sine, cosine is the value of x over 1, sine is the value of y over 1, we know that since it intersects at this point, square root of 7 over 4, and square root of 7 over 4 for the x value, and the y value is 3/4. Our r value is 1. Remember, that's key. So cosine of theta is equal to x over r, which in this case is equal to the square root of 7 over 4 over 1. Anything divided by 1 is just itself. So really, cosine of theta is equal to the square root of 7 over 4. Okay? Sine of theta, same exact thing. Sine of theta is equal to y over r. In this situation, it is equal to 3/4 or 0.75 over 1. Anything divided by 1 is itself. So sine of theta is equal to 3/4. Okay, done and done. So the point, and that comes straight from your key concept right here. All right, if theta is 120, p is cosine of 120, sine of 120. It's that same situation. So since the point p is at the square root of 7 over 4 3/4, we know that the cosine of theta has to be the square root of 7 over 4. Sine of theta has to be 3/4. Connor, what are you watching on your phone? Yeah. You're in the Zoom meeting on your phone?
I was.
Okay.
The copy was there too.
I get you. That's cool. That's cool. I was just making sure you're paying attention. Okay, so here we have the exact same situation. The terminal side of angle theta in standard position intersects the unit circle at the point P, which is the square root of 15 over 4. Y value is negative 1/4. Find cosine of theta and sine of theta. Remember, the key thing on being on the unit circle is that your radius value is always r. So the cosine of theta is going to be equal to our x value. The sine of theta is going to be equal to our y value, which looks like it's going to correspond with answer A. Okay, pretty simple there. Okay, here's the next thing that you're going to cover. This is like your periodic circular functions. Okay, so the question we're given is determine the period of the function. Okay, and when you're considering a period, you want to think about how long it takes to complete a full cycle. So what corresponds as a full cycle, right? It's where it begins to repeat itself. Okay, this case, we don't want to use x-intercepts. Okay, because you can see we intersect at pi over 6, we intersect at pi over 3, pi halves, 2 pi over 3, 5 pi over 6, pi, 7 pi over 6. What this is, as soon as we hit pi 3 here, you can see how we're positive on the y-axis, and we drop to the negative side, and then we come back positive. That is a full cycle. Okay, and the period of the function is how long does it take it to complete a full cycle. Okay, and that's with all values assumed. And if you look at this graph, it's just a pattern of itself. It's going to be positive, then it's going to be negative, then it's going to go back to positive again. Okay, and no other values change because they map onto themselves. So looking at this, we want to find the x value at where there is a full cycle. Okay, and the answer to that is going to be pi over 3. We have the x value of 0 here when it starts. We have the x value here of pi over 3 when it completes its cycle. One complete cycle is completed in the period. So the pattern repeats itself at pi 3, and 2 pi over 3, and pi, and so on. So therefore, the period is pi over 3. When you're talking about identifying the periods, it's all going to be about patterns. The same things are going to happen again. We're just trying to determine how long does it take for the same thing to happen. Okay, so like I said, it went positive, then it went negative, then it went back to positive. Okay, so this pi over 6 is a half cycle. Pi over 3 is full cycle, half cycle, full cycle, half cycle, full cycle. Okay, so here we're determining the period of the function. We start at a low point. Okay, we start at a minimum. And you can even, if you don't feel comfortable using this because it has an arrow, you could break it down right here. Start at this low cycle. You could start it at this high cycle, right? But so if you look when we're at pi in the x value, we're at a -1. Then we approach and we become positive at a +1 is the maximum. And then we drop back down to where we're negative and we hit our low point at 2 pi. So what's 2 pi minus pi? Well, it's just 1 pi, right? Or 1 pi radian. So this cycle or this period repeats itself every pi. 1 cycle, 2 cycle, 3 cycles would happen at 3 pi. Okay. This one, it says the pedals on a bicycle rotate as the bike is being ridden. The height of a bicycle pedals varies periodically as shown in of the function as shown in the figure. Notice that the pedal makes 1 complete rotation every 2 seconds. Make a table showing the height of a bicycle pedal at 3 seconds, 3.5 seconds, 4 seconds, 4.5 seconds, and 5 seconds. So here, we want to figure out where exactly did we start, right? Well, we started at the top, okay? And our pedal is rotating. The arrows should be drawn the other way. They rotate backwards, okay? So we're rotating counterclockwise here. We go 0 seconds, 0.5 seconds, 1 second, 1.5 seconds, 2 seconds. Okay, since we know this repeats itself, and we know it repeats itself every 2 seconds, it's given to us in the problem, how can we find where the pedal will be based upon that? Well, they give us that they want us to find it at 3 seconds, 3.5, 4 seconds, 4.5, 5 seconds. Okay, I could do this 2 different ways. The easier of the way is to kind of analyze just the period, right? So, and because it's a circular function, it's consistent. So it means that it's not changing. We're pedaling at the same speed for these 5 seconds. So when I hit 2 seconds, then I hit 2.5 seconds, then I hit 3 seconds, then I hit 3.5 seconds, then I hit 4 seconds, then I hit 4.5 seconds, then I hit 5 seconds, right? And I could just take that information and fill out a little table. So at 3 seconds, I should be where I am, where it says 1 second. So that's 4 inches. 3.5 seconds is 11 inches. 4 seconds completes my full rotation. I'm at 18 inches. 4.5 seconds, I'll be at 11 inches. 5 seconds, I'll be at 4 inches. Okay, and then I could go and carry on. And you can come up with that just by analyzing the graph. Okay, another thing that you can do to make it a little bit more formal is we can take these and subtract how long it takes us to make an actual period. So the question stated that it completes a rotation every 2 seconds. So 3 seconds is into my second rotation, right? Because it's greater than 2. So if I take 3 seconds and I subtract a full rotation, it takes me back to the initial, which is at 1 second. 3.5 seconds minus 2 seconds brings me back to where it's at 1.5 seconds. Okay, basically what I'm doing by subtracting 2 seconds on each one of these is I'm removing a cycle. And I'm trying to get back to the original position on the original cycle. Okay? At 4 seconds, minus 2 seconds, you can see that I just completed my first cycle. So this is the initial. Okay, 4 seconds represents 2 full rotations. Okay, so 4.5 seconds. By minus 2 seconds, you'll see that I'm at 2.5 seconds. Or the area of the pedal should be in the position that it was at 2.5 seconds. But that doesn't really help me because the information that was given to me is all based upon my first initial cycle. So what I can do here is, because at 4.5 seconds, I've completed 2 full rotations, I can subtract 2 seconds again to get that the pedal position should be when it's at 0.5 seconds. And then 5 seconds minus 2 seconds again is equal to 3. Doesn't really help me because that's still on my second rotation. So if I remove another rotation, the pedal position should be where it's at when it's at 1 second. Okay, and you can see that with this period, if we wanted to expand on this table, these numbers would just continue to repeat itself. Okay, you have a high point of 18 inches away from the ground. You have a low point at 4 inches away from the ground. And you have a midpoint between 11. So it's going to go 18, 11, 4, 11, 18, 11, 4, 11, 18, 11, 4, 11, 18, and so on. Because each rotation, the pedal doesn't change. Okay, the pedal height doesn't change. It's consistent. So this, the table on the left, will turn out to be the answer for our information. So at 3.0 seconds, the pedal is in the same location as 1 second, okay, which is 4 inches high. At 3.5 seconds, the pedal is 11 inches high. Okay, that's the same as being 1.5 seconds. At 4 seconds, the pedal is 18 inches high because that completes our first full cycle. Okay, at 4.5 seconds, the pedal is 11 inches high, which is equivalent to 0.5 seconds. And then at 5 seconds, it's 4 inches high, or our low point, which is where it was at 1 second. Okay, and you got to use the information that's given to you, right? They told us when it completes a full period. Okay, it's rotating every 2 seconds. It's complete rotation. So it started here, and then it rotated all the way to here. Okay, and from that information, since it's a consistent rotation, we can take that information and fill out our table. And this will repeat itself over and over and over again. You could break it down into 1,000 minutes if you wanted to. Okay, 1,000 minutes. Let's do that. So let's say they want us to figure out where the pedal position is going to be if somebody pedaled for 1,000 minutes. I can tell you that this person is very, very fit. Okay, because 1,000 minutes is a long time. But if I think about it logically, the cycle repeats every 2 seconds, right? So first, I want to find out how many seconds are actually in 1,000 minutes. So I'll multiply by 60 seconds. And I would get that in 1,000 minutes, there is 60,000 seconds. right? Okay, so now how many rotations did I make? Well, if it takes me 2 seconds per rotation, and I've been pedaling for 6,000 seconds, if I just divide that by 2, I'll get that I made 30,000 complete rotations. Okay, since it's a complete rotation, the pedal position would be at when I started pedaling at 0 seconds, or when I first completed my first rotation, or 2 seconds, which would correspond to 18 inches. Okay, it's cyclical. You can expand it as far as you'd like. You could do the same thing with 1,000,000 minutes, 2,000,000 minutes, it doesn't matter. Okay. Because a periodic function repeats itself. It's the definition, it has to. Okay, identify the period of the function. Okay, so the period is the time that it takes to complete one rotation. Okay, there, if we were paying attention in our word problem, it told us that we make a complete rotation every 2 seconds. So 2 seconds is the period to make one rotation. Okay, graph the function. Let the horizontal axis represent the time t, and the vertical axis represent the height 8 h in inches. Okay, so I'll go to my red pen if I can find it. There it is. Okay, so from my diagram, I know that I have high points of 18 inches, 11 inches, and 4 inches. Okay, those are really going to be my y values. So if I draw my graph, of course, they don't make it easy. So time is here as my horizontal or x-axis. This is the height of the pedal. Okay, and I'm going to use intervals of 0.5. So 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5. Okay, my height, I'm going to try to make it a little bit easier on myself, so I'm going to count by 2 on each one of these. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so then I can use my table, or I can use my graph. So at 0 seconds, what was the height of my pedal? What was that? 18 inches. Right there. Okay, at half a second, it was 11 inches off the ground. It's going to fall right there. At 1 second, it was 4 inches off the ground. Okay, at 1.5 seconds, back to 11. Then at 2, back to 18. That is the first cycle of my graph. Then at 2.5, drops back down to 11. 3 drops back down to 4. 3.5 is at 11. 4 is at 18. 4.5 is at 11. Okay. Oh, I messed up on that one. You guys let me get away with that? Because I was counting by 2s. So that is the graph. And you can see that the period is at 2 seconds, which is right here, because I've made a full rotation. And then every 2 seconds, I make a full rotation. So I have 1 period, 2 period, going on to the 3rd period, the 4th period, and 5th period. This is a full cycle. Touches all the points that it wants to touch, and then it starts back over. So the maximum of the height of the pedal is 18 inches. The minimum is 4 inches because the period of the function is 2 seconds. The pattern of the graph repeats itself in intervals of 2 seconds, such as from 3 seconds to 5 seconds. So that's the period that they chose. You can see at 3 seconds, it's supposed to be at its minimum height. At 4 seconds, it's back up to its maximum height. 5 seconds, it's back to its minimum height. That would also be known as a full cycle. You can determine cycles a bunch of different ways, but it's the key thing that it's always associated with the Y value. When does that Y value repeat itself? Okay, so the pedals on a trick oversized bicycle rotate as the bike is being ridden. The height of the bicycle pedals varies periodically as shown as the function of time. Shown in the figure, notice that the pedal makes 1 complete rotation every 4 seconds. So this person is pedaling slower. Okay, and you can see that it's a little oversized because we're at 30 inches, 20 inches, and 10 inches. So choose the correct table at showing the height of 0, 1 second, 2 seconds, 3 seconds, and 4 seconds. Well, at 0, we're 30 inches. At 1 second, we're 20 inches. At 2 seconds, we're 10 inches. Then we're back to 20. Then we're back to 30. So they give us tables. Let's look which one has that. So 0 should be our highest, right? Because that's our maximum value at 30 inches. So at 0 seconds, it's 30 inches. So right there, we can eliminate A, C, and D. Because they have time in seconds, the height is at 10 inches. So that's not representative of the diagram that they gave us. So our correct answer has to be B. And you can see that it just repeats itself. Okay, identify the period of the function. How long does it take to make 1 full rotation? Well, it was given to us in the problem, and from the diagram, you can see it's 0, 1, 2, 3, 4. We begin a new period every 4 seconds. So the period, or we begin a new cycle every 4 seconds. So the period of the function is 4 seconds. So choose the correct maximum height and minimum height of the graph of the function. If the horizontal axis represents time and the vertical axis represents the height in inches that the pedal from the ground. So our maximum height should be 30 inches and our minimum height should be 10 inches. Okay, because that is what is given in our diagram. Okay. So here is where we get to kind of put it back into trig areas, knowing our periodic function, okay? Because your sine and cosine and tangent and cosecant, secant are all periodic based upon the degree of the angle. So it says find the exact value of cosine of 690 degrees. Okay, so this is 90, this is 180, this is 270, this is 0 or 360. Okay, and I rotate 300 or 690 degrees. So riddle me this. How long or how many degrees rotation does it take for me to make a full rotation? 360, right? So 690 is greater than 360. Okay, so what that means is that I've rotated all the way around. Okay, but I need to figure out how much farther did I actually rotate. So I'm going to take 690 minus 360, and that is going to give me 330 degrees. Okay, what this is finding the coterminal angle. That's what it's called. Okay, so 90, 180, 270, 330 is going to fall in here, right about there. Okay, this is 690 degrees rotation or 330. Okay, if you remove that complete cycle. Okay, why do I want to remove the complete cycle? Because in order to find the cosine, I have to find the reference angle. Right? I have to find the reference angle. So how much farther would I have needed to rotate to hit that x-axis? Well, 360 minus 330 is equal to 30. So what this shows is that the cosine of 690 degrees or the cosine 330 degrees, because they're coterminal angles, they fall on the same terminal side, is what coterminal means. They always fall right there, back upon each other. That is equivalent to the cosine of 30 degrees. And then what do I have to do? I have to assign, whether it's a positive or a negative. It fell into quadrant 4. So that is where cosine is positive. So the cosine of 690 is equal to the cosine of 30 degrees, which is equal to square root of 3 over 2. Just like that. Okay, cosine of 330, they found it by using the reference angle and then assigning a positive or negative based upon the quadrant. Okay, here you got another good one. Find the exact value of sine. Why is that? You go into coterminal angles and then you do an easy one like this. That's ridiculous. Okay, the point I want to draw on to you on this one is that it's a negative rotation. Right? So when I set up my XY, I'm going to set it up to where it's kind of just a little different. Okay, but we're finding the sine of a negative 3 pi over 4. Okay, so the way that I set up my axis is just a little different because I know I'm rotating. It's a negative angle, so I know I have to rotate this way. Right, so this first axis is negative pi halves. This axis, once again, is negative pi. Now my positive y-axis is negative 3 pi over 2. So in other words, I flipped those two because I'm rotating the opposite way. Okay, 3 pi over 4 is bigger than 3.5. Oh, no, it's not. Okay, if I look at it in terms of a fraction, 3 pi over 4 is really 3/4 times pi. So that means I haven't touched this axis, right? If it was a bigger numerator and a smaller denominator, then I would have touched this axis, but I haven't. So I rotate it to roughly right about here. Okay, that's negative 3 pi over 4. So now, what must I do to figure out this distance or my reference angle? Well, so I can do it two different ways. I could take negative pi plus negative 3 pi over 4. Okay, find the common denominator, so that's negative 4 pi over 4 plus negative 3 pi over 4. And I would be left that I needed to rotate a negative pi force rotation. Okay, that represents this, representing the negative. So, but if I go this way, to hit my terminal side, I rotated pi fourths, right? Okay, that is just showing how much farther I would have needed to rotate on the negative axis in the negative direction to hit this axis. So the distance between here and here is pi force rotations. So the sine of a negative 3 pi over 4 is equal to the sine pi over 4, but I can't just leave it there. I have to figure out what the sine is going to be. So I fall in quadrant 3, where sine is negative. So the sine of a negative 3 pi over 4 is really equal to the negative sine of pi over 4. Sine of pi over 4 is square root of 2 over 2, which is equal to, so that would be a negative square root of 2 over 2. That's my final answer. What they're doing here, okay, you see how they did that? It's another way to attack this problem. More or less, since they added 8 pi over 4, they're starting on this terminal side, and they're adding a full rotation so that they could get a positive angle to do it. But if you just think about it logically, the distance between these two has to be pi over 4. Either way that you get it, has to be pi over 4. Okay, but what they've done is they've added 8 pi over 4, which is equivalent to 2 pi. So they've added a rotation to find the coterminal angle. So find the exact value of cosine of 660. What we would do is we would subtract 360. Okay, that would give us 300. So the reference angle of 300, that's going to be in quadrant 4. So cosine is positive. And it's going to be the reference angle of 60. So this one is B, 1/2. And find the exact value of negative sine of pi, 7 pi fourths. So once again, we'd rotate negative. We're going to cross the x-axis this time. And it is going to be in quadrant 2 with a reference angle of pi fourths radians. Since it's in quadrant 2 and it's pi over 4, sine is square root of 2 over 2. Done and done.